The Moon, our nearest neighbor in space, has always moved with us, shaping our nights and quietly influencing our world. It glows above us, pulls at our oceans, and remains one of the most captivating sights in the sky. Only a handful of humans have ever set foot there, yet its mystery still draws us in. Now, after years of looking away, humanity is turning its eyes back to the Moon with fresh ambition. We've landed. A simple phrase that once changed history forever. For some, the journey began long before rockets, back in childhood dreams. I used to look up and think, that's where I belong. Becoming an engineer meant chasing that vision, inspired by the pioneers of the past. Watching those first steps on the Moon wasn't just history, it was a calling. And today, that dream continues, carried forward by a new generation. In total, only 12 astronauts have ever walked on the Moon. Their journey was risky, complex, and deeply tied to global competition. But it proved something extraordinary. Leaving Earth was no longer impossible. Reaching another world, even one so close, became a reality. The next step isn't just reaching the Moon, it's learning how to survive and operate there. Humanity aims to build the skills needed to function beyond Earth, on another world. Mastering this will open the door to exploring the inner solar system, places that hold not only scientific value, but also potential economic opportunities. Benefits that may extend far beyond our generation. During the space race, both the United States and the Soviet Union sent numerous missions to the Moon. Some landed gently, others crashed deliberately for data. One of the final Soviet missions returned lunar soil containing traces of water. Since the 1970s, both science and technology have advanced dramatically. Global politics shifted, alliances changed, and new nations entered the space arena. More recently, private companies have also joined the effort. The possibility of water on the Moon sparked intense interest. Attention quickly focused on the shadowed craters near the lunar South Pole. In the 1990s, lunar exploration saw a strong revival. Japan led this return, becoming one of the few nations to place a spacecraft into lunar orbit again. Soon after, the United States launched a mission to map the Moon in detail. This mission gathered surface images, gravity data, and signs of possible ice. Evidence pointed to frozen water hidden in permanently shadowed craters. Follow-up missions expanded this research even further. They analyzed resources, mapped gravity fields, and even triggered impacts to uncover hidden materials. Europe also joined the effort with a compact but powerful lunar mission. This spacecraft identified key chemical elements on the Moon's surface. It also supported the theory that the Moon formed after a massive collision billions of years ago. A second Japanese mission continued detailed observations of the lunar crust. It delivered some of the clearest images ever captured of the Moon's rugged terrain. For the first time, high-definition visuals revealed the Moon in remarkable detail. And soon, another nation demonstrated its growing capabilities in lunar exploration. The mission also included advanced instruments, such as a NASA mineral mapping device and a dedicated impact probe. These tools played a crucial role in confirming the presence of hidden water near the Moon's South Pole. Just months later, NASA launched another mission, the Lunar Reconnaissance Orbiter, or LRO. Since then, it has been orbiting the Moon, collecting detailed data with highly sophisticated sensors. Its purpose is simple in theory, yet ambitious in scope, to build a complete scientific record of the Moon. By scanning the surface in fine detail, it creates a comprehensive atlas rather than a basic map. This includes terrain elevation, mountain structures, temperature variations, and mineral composition. It also investigates one of the most compelling questions: is there usable water on the Moon? To gather this data, the spacecraft flew in low orbit for extended periods. The results now guide engineers and planners preparing for future human missions. This robotic mission officially began operations in mid-2009. Its instruments were designed not only for lunar science, but also to improve our understanding of planetary systems. The onboard technology includes multiple scientific tools and experimental systems. Together, they generate data sets ranging from thermal maps to global surface models. But one objective stands above the rest: identifying resources like frozen water. All of this information helps determine where humans can safely land and build future bases. The ultimate goal is to support long-term human presence on the Moon. Data from LRO and other missions has revealed how the Moon's surface evolved over billions of years. It also explains why the Moon shares many similarities with Earth. Scientists believe the Moon formed after a massive collision early in Earth's history. After forming, it gradually cooled before being struck repeatedly by debris in orbit. These impacts shaped many of the large features we see today. Over time, constant impacts created the familiar cratered landscape. Studying the Moon also helps scientists better understand Earth itself. Unlike Earth, the Moon has no weather or plate tectonics to reshape its surface. This means its surface preserves a much older record of cosmic history. By analyzing impact craters, scientists can estimate how frequently collisions occurred in the early solar system. They can even infer the size of objects that once collided in space. One powerful technique used in this research is radar remote sensing. On other planets, like Mars, radar can reveal hidden layers beneath the surface. On the Moon, it helps scientists better understand impact structures. When a large impact occurs, molten material can spread across the surface. These formations offer valuable clues about the Moon's violent past. Molten rock spreads across the surface after an impact, forming wide-flowing layers. Over time, these layers are buried beneath debris from later impacts. But radar technology can see through those Z layers. It reveals hidden patterns, like streams of melted rock frozen in place. Alongside LRO, another mission was launched, LCROSS. Unlike long-term orbiters, this mission had a short and focused objective. Its plan was bold: crash directly into the Moon's south pole. Both the spacecraft and its launch stage were intentionally directed into a crater. From above, LRO observed the impact in real time. As debris was thrown into space, instruments analyzed its composition. Even during its descent, the probe continued collecting valuable data. The results confirmed that these dark craters contain useful materials. Scientists found clear signs that water exists on the Moon. Not just traces, but ice preserved for billions of years. These frozen deposits have never been exposed to sunlight. Meanwhile, LRO continued scanning the polar regions in detail. Repeated passes allowed scientists to map hidden hydrogen concentrations. Where hydrogen exists, water is likely present as well. This discovery could change the future of space exploration. Having water on the Moon reduces the need to transport it from Earth. It can be turned into fuel, breathable oxygen, and drinking water. It could even support agriculture and construction on the lunar surface. Another mission, originally designed for Earth studies, was later redirected toward the Moon. These spacecraft began analyzing the space environment around the Moon. They observed how solar particles interact with the lunar surface. The Moon's magnetic properties also revealed clues about its inner structure. Polar craters were found to have unusual electrical conditions. Charged particles from the Sun behave differently in these regions. Electrons reach the crater first, followed by heavier ions. This imbalance creates a powerful electric field. These fields may reach dangerous voltage levels. Hidden ice deposits could be shielded by these electrical effects. Another mission, called GRAIL, explored the Moon's interior. 2 spacecraft flew in formation, measuring gravitational variations. Their data revealed differences in crust thickness across the Moon. Scientists discovered that the Moon is not changing in just one way. In some regions, it appears to be slowly contracting. In others, it is actually stretching and forming new surface features. The discovery of these young surface features came as a surprise. Until then, most evidence suggested the Moon was slowly shrinking. But these new formations told a different story. Some regions appeared to be pulling apart instead. This raised an important question. How could both be happening at once? The answer lies in the Moon's long thermal history. Over billions of years, it has been gradually losing heat. When rocky planets first form, they are extremely hot. In fact, many of them were once almost entirely molten. As they cool, they naturally begin to contract. The Moon, however, followed a slightly different path. Only its outer layer melted, forming what scientists call a magma ocean. This created a complex balance of internal forces. Some forces caused the surface to compress. Others pulled it apart in localized regions. That's why we see both shrinking and stretching features on the moon today. One of the most exciting discoveries is that some of these features are relatively young. This suggests the moon may still be geologically active. The moon's crust is not uniform in thickness. On the side facing Earth, it is significantly thinner. On the far side, it becomes much thicker in certain regions. Its interior is only partially molten, not fully solid. Interestingly, the moon's mass is slightly shifted toward Earth. These findings reshaped our understanding of the moon. To study the moon further, NASA launched a mission focused on its thin atmosphere and dust. This probe analyzed how dust behaves above the lunar surface. At higher altitudes, very few dust particles were detected. But as it descended, particle activity increased dramatically. Close to the surface, dust became a significant factor. This has major implications for future landings. Both robotic and human missions must account for this environment. The probe continued lowering its orbit until its mission ended in a controlled impact. Meanwhile, new technologies for landing on the moon were being tested. One example is a self-guided robotic lander prototype. Designed to operate autonomously, it represents the future of lunar exploration. Once given a landing point, the system takes over, guiding itself safely to the surface. It scans the terrain, avoiding hazards and selecting the safest path. Similar autonomous landing systems are also being developed in Europe. Landing on the moon, especially near the South Pole, remains a complex challenge. It demands advanced navigation, hazard detection, and precision control. These missions are pushing the next generation of guidance technologies. But space exploration is shaped by shifting priorities. NASA's focus has gradually moved beyond the moon toward Mars. Meanwhile, budget constraints have slowed some European projects. This has created new opportunities for other nations to lead. Countries like China, India, Japan, and Russia are stepping forward. At the same time, private companies are entering the race. Their goal: first send robots, then humans back to the moon. China National Space Administration has already launched multiple lunar missions. Orbiters map the surface, followed by landers and rovers exploring it directly. Recent missions have even completed journeys around the moon and back. Their long-term vision includes a permanent human presence on the moon. The moon captures global imagination because it is visible to everyone. People remember historic landings and feel connected to them. It's a destination that feels both distant and familiar. Today, many nations are preparing their own lunar missions. Interest spans across continents, from Asia to Europe and beyond. Private competition has also accelerated progress. The Google Lunar X Prize challenged teams to reach and explore the moon. Beyond prize money, prestige became the real reward. Several teams emerged, each with unique ambitions. Some focused on future space tourism. Others aim to develop reusable lunar vehicles. And some are exploring mining opportunities on the moon. Resources like rare metals and isotopes could hold great value. One company has even secured a launch using a Falcon 9 rocket. Reaching the moon is a milestone, but staying there is a far greater challenge. Early missions lasted only days, carefully timed to avoid risks. Future explorers will need to survive much longer in a harsh environment. Living on the moon will require entirely new strategies and technologies. To survive on the moon, we first need to fully understand its environment. Only then can we develop ways to protect both humans and equipment. One major concern is the intense radiation found in space. This radiation can affect electronics, communication systems, and human health. Understanding these risks is essential for long-term missions. Future missions aim to identify the safest locations on the lunar surface. They will also help determine how we can return and stay there safely. One key factor is access to continuous solar energy. In the short term, solar power could be the most reliable resource. Other resources like water, ice, and minerals may take longer to fully utilize. Still, their potential value is enormous. They could support life, fuel production, and construction. Major space agencies like NASA and European Space Agency are already planning lunar bases. Private companies are also contributing new ideas and technologies. As more data becomes available, these plans continue to evolve. One promising approach is the use of 3D printing for construction. Structures could be built directly using materials found on the moon. Despite the challenges, many organizations are targeting the next decade for lunar bases. Some missions will focus on science. Others will explore commercial and tourism opportunities. Future crews may include not just scientists, but also specialists from other fields. Looking back, missions like LRO may be seen as the first step toward a larger transformation, a moment when humans began to move beyond Earth permanently. The Moon could become the starting point for deeper space exploration. This time, the goal is not just to visit, but to stay. Every new mission expands our understanding of the Moon. It also helps us understand how other rocky planets evolved. Each discovery adds another piece to the history of our solar system. With advancing technology, our knowledge will continue to grow, and with it, our ability to explore worlds beyond our own. It all begins with understanding and the power of heat and energy.